From the pixels that make up the very image on your screen right now to the complex financial models that drive, well, everything, there's this hidden language that's organizing our world. And today, we're going to decode that language. We're talking about the matrix. It's an incredibly powerful tool, and we're about to see just how it can take really messy problems and turn them into super elegant solutions.
Okay, so here's our game plan. First, we're going to start with the absolute basics. What even is a matrix? The fundamental building blocks. Then we'll get into the rules of engagement, basically how these grids of numbers play with each other. After that, we're going to uncover this special secret number that's hidden inside every square matrix. It's called the determinant, and it's kind of like a key. And then finally, we'll use that key to solve a classic math puzzle, a system of linear equations. All right, let's jump right in. Section 1, data's building blocks. So before we can do any of the cool stuff, like solving puzzles or complex operations, we really need to get to the heart of it. What exactly is a matrix? I mean, at first glance, yeah, it just looks like a box of numbers. But it's that super precise, organized structure that gives it all its power. So at its very core, a matrix is really just a way of organizing information. Seriously, think of a spreadsheet or, like I said, the grid of pixels on your screen. It's just a rectangular grid of numbers set up in rows that go across and columns that go up and down. And what's cool is that this simple grid gives every single number inside it a very specific locked-in address.
So we usually give a whole matrix a name with a capital letter, like A. Simple enough. But what about the numbers inside? To find a specific one, we use this little address system, A sub ij. The I tells you which row it's in, and the J tells you the column. So if you see A sub 23, that's not just some random number. It's the one that lives in the second row, third column. Super specific. This is basically the grammar of how we talk about matrices.
Okay, now things get really interesting when we talk about a special kind of matrix where the number of rows is the same as the number of columns. We call this a square matrix, for obvious reasons. And inside this perfectly balanced shape, two really, really important paths show up. We call them the diagonals. So you've got the first one, the principal diagonal, which zips from the top left corner all the way down to the bottom right. And then you have its counterpart, the secondary diagonal, which goes the other way, from top right to bottom left. Now, these aren't just random lines we're drawing. Trust me, these paths are super important for some of the calculations we're going to do in just a little bit, so keep them in mind. Okay, so we've got the basic structure down. We know what a matrix looks like, but, a structure isn't very useful unless you can actually do something with it, right? So in this next part, the rules of engagement, we're going to dive into the basic operations, how we add, subtract, and multiply these things to really start using their power.
All right, adding and subtracting matrices is, thankfully, pretty straightforward. There's really only one major rule you have to remember. The matrices have to be the exact same size, same number of rows, same number of columns. If they are, it's super easy. You just add or subtract the numbers that are in the same exact spot in each grid. That's it. Multiplication, though, that's a whole different ballgame. It has a much stricter rule. Here's the deal. To multiply matrix A by matrix B, the number of columns in the first one, in A, has to be the exact same as the number of rows in the second one, B. Think of it like the two inner numbers have to match. If they don't, you just can't do it. Multiplication is impossible. But if they do match, the new matrix you get will have the dimensions of the outer numbers, the rows from A and the columns from B.
So how do you actually calculate the numbers in that new matrix? Well, it's this methodical little move called the row by column operation. To get just one number in the final answer, you take a whole row from the first matrix and a whole column from the second one. Then you multiply the matching pairs of numbers, one by one, and add all those little products together. And yep, you have to do that little dance for every single spot in the new matrix. Okay, now we're moving on to one of the most fascinating ideas in all of matrix algebra. It turns out that hidden inside every single square matrix, there's a special, unique number, a single value that tells you a ton about the matrix itself. This number is called the determinant. And you'll see it's like a secret key that unlocks all sorts of deeper properties and solutions. So if you want the formal definition, the determinant is a scalar value that you compute from the numbers in a square matrix. But a better way to think about it is like this. It's a single number that basically boils down the very essence of that matrix. You want to know if a system of equations has one unique answer, or if you can invert a matrix? The determinant is what holds the answers to these really important questions. For a little 2x2 matrix, finding this key is super easy. Remember those diagonals we talked about? You just multiply the two numbers on the main principal diagonal,
Then you multiply the two numbers on the secondary diagonal. And you just subtract that second result from the first. Boom. That one number you get is the determinant.
Now, for a bigger 3x3 matrix, we use this really clever trick called the rule of Saris. Here's what you do. You take the first two columns of the matrix and just copy them over again to the right side. This little move is genius because it creates 3 full principal diagonals and 3 full secondary ones. Then, just like before, you multiply the numbers along each diagonal, add up the totals for each group, and subtract the secondary group's total from the principal group's total. That's your determinant.
Okay, so we know what matrices are, we know how to do operations with them, and we know how to find that secret key, the determinant. We're ready to put all these tools to work. We're shifting from just the theory to a real-world application, and we're going to tackle a problem you see everywhere, from physics to economics, solving systems of linear equations. This is where the amazing organizational power of a matrix really shines. So what even is a linear system? Well, it's really just a bunch of equations that are all tied together because they share the same variables. And the big goal, the whole point, is to find that one single magic set of values for x and y that makes every single one of those equations true at the exact same time.
Now, sure, you could try to solve this with the algebra you learned in high school, with substitution and all that. But honestly, that can get super messy and complicated, especially if you have more than just 2 variables. So that leads to the big question. How can we restate this whole problem using the clean, super organized language of matrices?
And the answer is just so elegant. We can literally break the whole system down into 3 separate matrices. First, you pull out all the coefficients, the numbers attached to the variables, into a matrix we'll call A. Then you put the variables themselves, x and y, into their own matrix, X. And finally, you take the numbers on the other side of the equal sign and put them in a matrix B. And just like that, you've turned this messy jumble of equations into one single beautiful expression, A times X equals B. And that brings us to the grand finale, cracking the code. We've successfully translated our problem into matrix speak. We have our equation, A times X equals B. The goal now is to solve for X, to find those unknown variables. And guess what? We are totally equipped to do this now, using 2 different but equally powerful methods.
So our 2 paths to the answer are Cramer's rule and Gaussian elimination. Think of them like this. Cramer's rule is like a direct formula. It relies almost entirely on those determinants we just learned how to calculate. Gaussian elimination, on the other hand, is more of a step-by-step process. It's more hands-on, where we actually change the equations around to make them way easier to solve.
Cramer's rule is basically a recipe for finding the answer. Step 1, you find the determinant of your main coefficient matrix, A. We'll call that the main determinant. Step 2, to find, say, the value of x, you make a new matrix. You do this by taking that original A matrix and swapping out the x column with the numbers from your B matrix. Then you find the determinant of that new matrix. And the answer for x is just the new determinant divided by the main one. You just do that same thing again for y, and you're done.
Gaussian elimination feels more like you're solving a puzzle, step by step. First, you create something called an augmented matrix, which is just a fancy way of saying you take your coefficient matrix A and stick the constant matrix B onto the right side of it. Then, using a few legal moves called row operations, your whole goal is to get a bunch of zeros in the bottom left corner. This turns it into a triangular shape that's super easy to solve. The last variable just pops out, and you find the rest by working your way back up. They call it back substitution, which is a perfect name for it.
Yeah, this is the whole goal of Gaussian elimination right here, to get this triangular shape, or what mathematicians call echelon form. See that triangle of zeros in the bottom left? That's the magic. Because what that means is that the very last row is now a super simple equation. It's something like 0x plus 2y equals 4. Well, hey, with only one variable, you can solve for y in a snap. And once you have y, that's the key that unlocks everything else.
So, we've seen how matrices can take a messy system of equations and solve it so cleanly. But that is honestly just scratching the surface. This fundamental idea of organizing data into a grid, it's literally everywhere. It's silently running the computer graphics in the movies you watch, it's optimizing the shipping routes that bring packages to your door, and it's modeling entire economic systems. The matrix isn't just a math concept, it's one of the most powerful tools we have for making sense of our incredibly complex, data-filled world.